While SOFIA is not a new observing platform, I thought it was important to bring to the attention of the PCME community the opportunities of SOFIA and let you know about some future plans for new capabilities on SOFIA, and along with a few brief highlights that I'll try to squeeze in. So SOFIA is a 2.5 meter telescope operating in the stratosphere. And there's a large wavelength range here. Let's see, where infrared light is blocked from our view on Earth from about 25 to 350 microns due to the Earth's water vapor. So SOFIA flies in the stratosphere at about 1,300 feet. Wait, my mouse is stuck here. Let me go back here. Okay, here it is. Here's SOFIA coming in at 13,000 feet. It gets us above about 90% of the atmospheric water vapor. So at least for the next decade, SOFIA will be the only facility that provides access on a regular basis to the far infrared sky. Unlike space missions, of course, SOFIA can repair, upgrade, and replace its instruments for these as the science priorities evolve and as technologies change and improve. Recent activities have been carried out to evaluate SOFIA's science and instrument future. The objectives being to plan out SOFIA's roadmap for the next 5 years, and also with a 10-year vision. So last year, NASA's SOFIA Ames group carried out these 2 workshops. The first one exclusively to solicit the community's needs and their desires of what they want to do now with SOFIA. And the second workshop was just to bring in all the instrument concepts that could meet the science cases that were brought up. And out of these 2 meetings came the SOFIA instrument roadmap, which I'm going to report a little bit about. And so the German SOFIA Institute also wanted to get the European perspective on this. And so this year they've been carrying out these 2 meetings, similarly like was carried out last year with the NASA team. And this summer there was the workshop to discuss the Europeans' ideas on their science cases they want to push. And then in November will be the instrument solution workshop. And out of these 2 meetings will come a white paper, and then all will be coordinated with the NASA German and SOFIA teams. So the current instrument, just very briefly, the current instrument suite of SOFIA consists of 5 instruments, and you can read about more details and their sensitivities here. The great instrument is here is the resolving power on the y-axis versus wavelength. The great instrument is the high spectral resolution heterodyne instrument containing these individual spectral bands throughout 60 to 600 microns, aimed at specific far infrared cooling lines. And you see the resolution is about as high as ALMA is. And then there's FIFI-LS, which is an integral field far infrared spectrometer, which has lower spectral resolution than great, but has a continuous spectral range between 50 and about 200 microns. It's a 5x5 pixel array, so it's a good mapping tool. EXIS is a high resolution near infrared spectrometer covering about 4 to 28 microns here. And it actually has higher spectral resolution than the JWST. Forecast is a dual channel mid-infrared camera spectrograph, which covers from 5 to 40 microns. And then down here, HAWK Plus is the newest instrument for SOFIA. It's a far infrared camera and imaging polarimeter, and it's one of the most popular instruments on SOFIA. Lots of proposals are coming through with science cases for it. So it's designed to allow both total and polarized flux imaging in these 5 bands between 50 and 250 microns. So SOFIA's instruments, they really fill the gap between ground-based telescopes such as ALMA and NOEMA and other single dish telescopes, and currently the JWST about to launch. And so to highlight some of the capabilities, I'm just going to show some of the programs currently in progress, and starting with Orion. And this is a 1 square degree SOFIA great map of Orion in the C+ line. And on the left here is the integrated intensity. And you see the little box insert. That's the size of the map that Herschel Hi-Fi was able to do. So SOFIA's great instrument is about 50 times faster than Herschel Hi-Fi in mapping the ISM and the C+ line in the galaxy. And this fast mapping speed plus the resolving power really gives you the opportunity to look into the kinematics and the dynamics of these cooling lines in full complexes. And on the right here, you see the velocity of the different structures of the C+ emission. And one of the key results from this C+ map is that stellar winds from the trapezium cluster there dominates the feedback process in Orion, not photodissociation or photoionization. And Nicola Schneider highlighted these science results in her talk yesterday also. So this Orion project inspired a new legacy proposal called Feedback that Nicola and Xander Thielens are the co-PIs for. So SOFIA has these calls for legacy proposals. A few each year are chosen. And they're proposals, projects that need up to 200 hours of observing time maximum to do over 2 years. And so this particular program features these great maps of C+ and O1 in 11 well-studied star-forming regions to study the massive stellar feedback in these star-forming regions. And here you can see in the Eagle Nebula this really cool velocity structure that was mapped out with a great instrument. It's still in progress, and some of the initial C+ and O1 data cubes, I believe, are available in the archives for the community. The thing about legacy programs is there's no proprietary time, so they're for everybody right away. Enrique Lopez is leading a team to study the magnetic fields in nearby galaxies. And you can see from these images, if you can see that much, that the magnetic fields show a wide variety of global structures. Here in M82, you can see the magnetic field lines are aligned with the galactic winds emanating from M82. And here's Centaurus A, which is a merger of 2 galaxies with a central black hole. And the magnetic field lines are aligned with the disk of this galaxy. I don't know if you can see them very well. And M51 is pretty spectacular. It shows the magnetic field lines swirling with a spiral structure. And so there's lots of proposals using Hawk Plus and legacy proposals too. And of course, there would be a big proposal to look at filaments and magnetic fields. And so we are conducting a new large survey simultaneously of C+ and O3 using FIFI-LS in the Magellanic Clouds. And we're mapping this southern molecular ridge here, which is just south of 30 Doradus. And this follows a pilot study we did of a big 30 Doradus map with FIFI-LS that was published by Melanie Chavance recently. This is a 1 degree by ½ degree map we're making. And it's a region that's been also mapped with ALMA and other single dish telescopes. But the molecular gas, even though there are many very active star forming regions here, there's not much molecular gas traced by CO. So this study, one of the things that's going to be come out of it is quantifying the CO dark gas mass using the C+ line. And what's controlling the presence of the CO dark gas versus the CO bright gas? Because there's huge environmental changes in this region that we can study. So SOFIA is also a powerful tool for astrochemistry work. SOFIA Great claims the first detection of helium hydride in space at 149 microns in the planetary nebula NGC 7027. Helium hydride is the first molecule that was formed after the Big Bang, and it plays an important role in the pathway to molecular hydrogen in the early universe. And it was recently published in Nature by Ralph Whiston. And then there's a new program from Cycle 8 that just started this year, HiGal. This is led by David Neufeld and Peter Schilke, characterizing the galactic ISM with a variety of these hydrides. They're looking toward 22 background continuum sources within the galactic plane. And it took its first data earlier this year. It's using these absorption line spectroscopy of these hydride molecules to constrain astrochemical models that been created for the turbulent interstellar medium. So this should be interesting. And so the SOFIA roadmap plan has been presented to NASA. It's the result of the community input to the workshops last year. And NASA is investigating implementation aspects of it. And it's public and you can see it online. And in this roadmap are contained 9 specific science cases here. And you can see all your favorite ones listed here. Star and planet formation ideas, astrobiology, path to life, and nearby galaxy evolution. And for each of these 9 science cases, required observing parameters were detailed out, what species, what spectral spatial resolution, and then also the new instruments that are proposed, the capabilities for the instruments that are necessary to meet the science cases. So this is in the report and you can study it in more detail. So the roadmap actually is made up of 3 different steps that are laid out sequentially in this timeline plan. I'll show more about the specific steps that are listed here, but just in summary, the first step is a upgrade of an instrument, and HAWK+ was chosen after a call for these different upgrades. It's something that can be done pretty quickly. And then step 2 consists of, will be one of these 2 concepts that are brought up for a new instrument that can be realized in the next 5 years. And step 3 is something that it's a longer time frame. This sequential approach takes us into the next decade for when this new instrument call should take place. So the first step is the instrument upgrade. This has already started, replacing HAWK+ detectors, which will increase the mapping speed for magnetic fields by a factor of up to 4. And it would enable 2 of those 9 science cases I just showed. So NASA Goddard and NIST are currently submitting a joint proposal to do the work, and the SOFIA missions operations will be a part of the implementation team for this. And one of the concepts for step 2 is a direct detection 30 to 120 micron spectrometer, which is quite a popular need to enable 5 of the 9 science cases that have been brought up. One of them being a fun one to measure the molecular mass of the protoplanetary disk using HD as a proxy. And so because of the sensitivity needed, the concepts are for either, of course, TES or KIDS detectors. And actually, this does resemble a bit the objective of the recently terminated Hermes instrument. And another concept in this step 2 of the roadmap is a terahertz mapper to build a 100-pixel heterodyne array built on the success of the GREAT instrument. And here are the current arrays, the hexagonals for the GREAT instrument. This is the C+, the C+ array of 14 pixels, and the 01 63 micron arrays here. And you see how huge this idea of a terahertz mapper would be to utilize SOFIA's large focal plane. This is pretty highly demanded by current users. And the third one takes us to the next decade and past current ideas for far infrared balloons and and other telescopes that are taking place of far infrared JWST. So discoveries from SOFIA and all these other observatories would undoubtedly change the scientific landscape and priorities of the community. So that would mean that additional community input would be needed to call for a new plan for a new instrument to better define this step, to take it to the next decade. And so in summary, SOFIA has a bright future, I think, to make discoveries specifically in the PCMI science domains here. These legacy program ideas should be really attractive to everybody. You can build large cohesive science programs and the data goes into the public archive right away. And SOFIA can, because of the timeline, it could pave the way to origins if that's chosen. And so the instrument in summary roadmap projects a 10-year future to enable discoveries via an instrument upgrade, new instrument concepts. And I didn't go into the detail, but there's planning to be twice as much observing time available to enable more research to come out of SOFIA and more Southern Hemisphere flights, because there's often only one flight in the Southern Hemisphere a year. And so if you want to, you can register if you want now for the next SOFIA workshop, which will be in November. And that's it.
Thank you. So we have 2 questions. Jérôme?
So how do you explain the difference in the magnetic field orientations in M82 and Cygnus A?
So you're kind of muffled. I didn't quite hear it. I don't have the. Could you say it again, clear? Sorry.
How do you explain the difference between the orientation of the magnetic fields between M82 and Cygnus A?
I have no idea. I'm not. So people in the audience probably have closer contact to the science papers that came out of those. Yeah, I think I don't know if that we know that. I mean, the orientations are so different.
We're going to take the question of Laurent Paganich.
Yes, I was a bit surprised that in your roadmap there was a reappearance of the HD receiver, since there was already one in the great German receiver on board, and as far as I know, no science has been published from that receiver. And the main reason was that the sky's transparency at SOFIA altitude was not good enough for that. So do you know why they are trying to put again this receiver in the future?
So it's also a question of sensitivity here. This would, really improve the sensitivity a lot. And yeah, the location of the atmosphere is challenging, but you can go higher up. I think they didn't try hard enough, as far as I know. I know that was attempted.
I can comment maybe on that, Laurent, also. For the heterodyne, at least, the HD receiver indeed atmosphere is one thing, but the instrument sensitivity was not as good as it can be. It's probably 2,000 or 3,000 K noise temperature, and it could really be made 3 times better. So that's quite feasible nowadays. So the sensitivity could be improved easily.
Yeah, and I sort of remember that their system temperature was much worse. Well, their receiver temperature was much worse than what they expected at the start.
Yes, it was because there was not enough local oscillator
low
power.
power.
We were using diplexers, so it can it can be improved a lot.
That's right. That's right. I forgot.
So Laurent, how come you're not asking about the carbon footprint of with their increased number of flights they want to do now?
Yeah, I've been thinking of it. So yeah, I was thinking of it. Just they are going to fly with hydrogen instead of kerosene.
Well, they're talking about more flights, so you
yeah,
know,
but more flights with molecular hydrogen to power the plane, of course.
Yeah, I don't know how long we're going to get away with it because right now, if you do, they do 10-hour flights. If you do 4 10-hour flights, you have less research time than if you do 5 8-hour flights. You get up to the stratosphere quicker.
So I propose to thank you, Sue. I propose to move on.
Okay.
And Laurent actually is the next speaker anyway. And he's going to talk about the Laurent.